So good morning. Can you see both myself and the flip charts?
Yes.
Nice. So we can start another lecture today. As far as I remember, I have promised you to talk a little bit about a simple method which is partly numerical, partly involves some analytical work. That's the way. So it's not as easy as finite difference in steady state. And what we will investigate is the simplest waveguide. But we will not investigate it only as a waveguide which has lossless, ideally conductive metallic walls and ideally non-conductive dielectrics inside. Well, that's simple and that has analytic solution. What we shall do is we would investigate the simplest case but with the presence of losses. So what we have in fact, we have a parallel plate waveguide. We have two planes that are conductive and are perfectly parallel, and inside, in between them, there is some dielectric. So this is the ideal version. With the ideal version, you have the electromagnetic field only inside. It propagates in a lossless way because there is no conductivity inside, while the conductivity at the boundaries is infinite. So there is no heat anywhere. But we will investigate a little bit more interesting case. We will have, in fact, metallic or conductive walls of finite thickness, and then there is the outer space. And let's investigate this as a general structure. So, well, we will start with the ideal waveguide, which has no losses here, perfectly conductivity here, and no field outside. But let's switch to a general description. We have some material here, some material as another layer here, and outer material which reaches the infinity, which also has some permittivity, permeability, and conductivity. We will then find out the solution for electric field strength, magnetic intensity, or whether you want field densities, currents, and whatever. Now, having the material, we will always have mu, permeability, permittivity, and conductivity for each of the materials. So let's mark them like material 1, material 2, and material 3. Within each of those materials, there should be, or there exists, a wave number for the electromagnetic wave. And after all, the electromagnetic wave should obey an important equation. We have no sources there, so for harmonic field behavior, we should know that there must be satisfied the condition of the wave equation, for example, for electric field strength. That would be Laplace applied on E plus k squared E is 0, where k squared stands for minus j omega mu j omega epsilon plus sigma. Omega is the angular frequency. So this is the situation. But within each of those regions, we have different k. So we have k1, k2, and k3, depending on the material properties. And here's the frequency. Now, having this in mind, we can again remember this equation. In fact, we can rewrite it using a decomposition of the vector k into its three components, so that we will have k squared, which is k x squared plus k y squared plus k z squared. So this is a decomposition of this equation, meaning that the wave can propagate in an arbitrary direction. Its propagation is bound by the k, and it then would project into x, y, and z directions or unity vector in this manner. So the total magnitude of k should be in relation with its components. Those components, for example, could not be bigger than the total wave k number. So now this is what we know. We have a small problem. For example, we have, if we denote one of the axes like z, and we would think about propagating the wave along the waveguide in the z direction, then we could denote this part kz, and in fact we could break the equation into two parts. We would have in the z direction we would have the dependence, for example, for the field vector E as a function of z. That would be some E at the origin, I would mark it E0, times E raised on minus j k, that's the k in the z direction, times the coordinate z. This would be a wave propagating from minus infinity in z to plus infinity in z. But in this manner we can do a little bit work in this equation, because Laplace means a sum of second partial derivatives against x, y, and z. One of those, the derivative against z, we can elaborate because we know the exponential, we can derive it. Deriving this would give us E0 times minus jkz E minus jkzz. So deriving twice, we know now that so this is the result. If we carry out second derivative against z, we get again this, and therefore we would be able to simplify this equation and cancel out one of the derivatives. But anyway, there is a second note I would like to raise. We have the wave equation for electromagnetic field strength. In fact, this means this is an abbreviation because we have written E, but in fact this is a set of three equations. The same equation could be written for the component of the field vector E into the z direction, x and y. So there are three equations hidden in this one, and that's not the full characterization of electromagnetic field. There are also components of the magnetic field. There are three possible components in Cartesian coordinates. So in fact, in this manner we would have a set of 6 equations. That's rather much. But what we can do is to make use out of Maxwell equations. Surprisingly, those 6 equations or those 6 components, Ex, Ey, Ez, Hx, Hy, and Hz, are not independent. In fact, you can choose 2 of them that fully describe the rest. Combining Maxwell equations all together would give you a result, which I will just bring for a moment. So if we get 2 components, in this case the electric field strength in the z direction and the magnetic intensity in the z direction, as principle, we can relate all other components of the field to those 2 ones. So, in fact, we have a set of equations that can give us all other components based on those 2 components we will find out. Moreover, from this set of equations you can see that, in fact, this is 2 independent fields. If you have Hz, which is 0, there still will be some electromagnetic field generated by Ez, and Ez generates no field in Hz component, and vice versa. So those are 2 independent fields that you can handle as created by the component of the electric field strength in the z direction, 1/2 of the field, and magnetic field intensity in the in the z direction, like the second part of the field. And yes, in waveguide theory, which some of you have studied already, the Ez field generates something which is called transverse magnetic waves, and the Hz generates something which is called transverse electric waves within a waveguide. So we now have a means to find out this equation or the solution within only 2 components, and for the sake of simplicity we will start with one of the modes, because those are 2 independent tasks: transverse magnetic waves, transverse electric waves. So for the beginning we can start the job with setting Ez to a small value, then Hz to 0, and vice versa, and we can do the solution. In fact, if we have dealt with only perfect conductor, we would be ready at this moment, because now we would say, okay, so if this is a perfect conductor and we would have an Ez, for example, as the property we would like to solve, then we are pretty sure that it must obey the rule that at the metallic walls it becomes a 0 because it's a tangential component. Then we will be having this as 1/2 of a sine or cosine, depending on where you choose your coordinate system start, and we will just use that set of equations to generate other components of field from it. That would be in the case of perfectly conductive walls. We could possibly use it for classic metals, because still the component at the surface of a metal, the tangential component of electric field strength, is quite small. But we wanted now to get another solution which is a bit more tricky. And now we involve 3 materials. 3 materials with different velocity of propagation of light, or wave vectors, which means the same. So now we have three materials at which the light or the electromagnetic wave propagates with different velocity, namely inside the waveguide walls, and outside the waveguides. So now we would have to find out what we know about the field using the law of physics. Then we would have to somehow use it to generate equations, and we will have to solve them. The first part is analytic. The second part, solution of those equations, is numeric because there is no analytic solution. So then this is why we talk this in this subject. So let us start with what we do know about the field. Well, first, we know the propagation constants of each of that material. So we know that within each region, the field should obey the wave equation. Second, we know that the field in the waveguide should, at each boundary, fulfill boundary conditions. In fact, we have more boundary conditions than necessary to find out our solution. So now I will use this as a symmetric case. Let us consider only symmetric cases. Because of the symmetry of the geometry, the field should be symmetrical or antisymmetrical. That is, we could have here half cosine if this is 0 in the vertical direction, or we could have here half sine, which would be symmetric or antisymmetric field. And let us now treat only one half of the structure. So we have this axis of symmetry. We have at the distance of A, we have the beginning of the plate or layer, second layer. So this is the layer 1, layer 2, and we have layer 3 upstairs. Now we have those boundary conditions we know. So the field should obey all boundary conditions, that is, the tangential component of the electric field strength must be identical at both sides of the boundary. So between the inner material and the outer material at the height of A, both electric field strengths within the second layer and within the first layer must be identical. That's a boundary condition, tangential field components. The second point, for the magnetic field intensity H, the same should hold. The tangential component should be 0. Now, the difference between the tangential components should be 0. Second, we could derive equations for tangential components running into or out of the paper. Then we have another set of boundary conditions. And finally, we could derive conditions for normal components of E and H, or E and B, however, and that's another set of boundary conditions. The same situation is at the boundary, at the upper end of the metal or material layer. Again, field components that are tangential here and here must be strictly identical. we could also use normal field components normal to the boundary, and then there should relate in a ratio given by their dielectric or magnetic properties. So again, we could derive a condition that should hold here. And finally, we have one more condition. Our field should be bound so that the energy of the field is not exceeding any limits. That means that we should strictly require that somewhere upstairs in the infinity the field gets zero. That is, it should decrease its values with increasing the distance from the axis in the outer layer. This is an important condition, because once you allow infinite energy, you get any nonsense you try to get. So this is what we have from the physical point of view. Now, questions? Is there any problem with Emil Tivoniak connection?
Vypadá to tam.
That's strange, because he's a member of the group like anybody else. Well, but he is here. Yeah, he's connected, so there should not be a problem. Okay. Any other questions, please? So now we have collected the set of let's say physical bounds on our solution. We would like to find a solution that